I'm going to try and talk about a, there's that, okay. Which? There we go. Okay. All right, yeah, so I'm going to talk about star formation and nuclear activity in a range of galaxy masses, and basically, yeah, try and tie together some of the multi-wavelength studies that I've been doing that Francois mentioned. And I should acknowledge some of my collaborators here, a few of whom are in the room, Sabrina and Lee. And basically, you know, different aspects of this have been X-rays and radio observations have been helped by these folks. So I'm going to start by giving a kind of introduction to the galaxy evolution and spend a little bit of extra time on molecular gas tracers and what I think they can say about galaxy evolution and probes of nuclear activity. And then I'll go into more detail about that and talk about some both resolved and galaxy integrated projects that I've worked on, trying to tie together dense gas tracers and AGN. And then I'll switch gears for a little bit and talk about a technique that I've been trying to apply more and more widely to basically use simulations to better understand the benefits and limitations of common observational techniques. And I'll explain what ground truthing is when I get there. And then I will wrap up by talking about starburst and dwarf galaxy mergers, which I think is a very interesting topic that's becoming more and more feasible and perhaps more and more useful as well. So the kind of stage I want to place this on is to look at kind of a bulk galaxy property and to look at the galaxy main sequence. So if you plot star formation rate as a function of stellar mass, then you find that basically a large number of galaxies lie in this kind of narrow sequence there. And then there's a smattering of galaxies down here that are, of course, forming stars much more slowly or not at all. If you look at this in morphological or color space, you find that galaxies tend to also kind of cluster in this space based on their color morphology. The main sequence galaxies tend to be kind of blue star-forming disk galaxies. Those objects below the main sequence tend to be kind of redder galaxies, often elliptical galaxies. And then as you go above the main sequence, the things that are kind of forming stars much more vigorously are the galaxy mergers. And I should say this is a redshift 0 main sequence plot, but the main sequence has been found to roughly maintain itself through redshifts 3 or 4. So if you want to ask how galaxies move in this space, kind of to first order, they just kind of grow up along the main sequence and kind of move from the lower left to the upper right. If two galaxies run into each other, they have a brief period of time where they kind of jump up above the main sequence, start forming stars at an accelerated rate, and then presumably settle back down onto the main sequence. If they exhaust that gas supply, or if there's an AGN or some sort of large feedback event that removes the gas from the system or prevents it from further forming stars, either by just heating it up or some sort of continual energy injection, you can actually quench the galaxy, and then it kind of falls off the main sequence and turns into this kind of red and dead elliptical. So the sample I'm going to primarily use to look at this is the Great Observatory's All-Sky Lurg survey, which is an infrared selected sample of galaxies picked from IRAS. There's a flux and luminosity cut such that these are basically the most nearby, most luminous galaxies in the kind of local universe. So the biggest and baddest star-forming galaxies and AGN hosts. This is a kind of a montage on the right of a few of the galaxies. You can see there's a large fraction of them that are involved in major mergers and interactions. The GOLS sample has this lovely multi-wavelength data set that basically stretches from radio through X-rays. And we can essentially probe all of these interesting physical processes in galaxies, the obscured and unobscured star formation, the presence of AGN, the interstellar medium properties and content, and then also the dynamical state. And Francois mentioned my identikit modeling, which is firmly in the dynamical state. I won't talk about that today. I'm going to focus on the AGN and the ISM properties. But the beautiful thing about this sample is we have extreme galaxies that are nearby, and we can study them at high resolution and basically look for signatures of energy injection to the ISM from AGN star formation and basically explore how these galaxies grow in kind of gory detail. In terms of the molecular gas itself, we can't observe cold molecular hydrogen because it doesn't emit essentially when it's a few tens of Kelvin. So we're forced to use tracer molecules. And the emission from tracer molecules is typically rotational transitions in the millimeter and submillimeter. And to kind of first order, you can think of this as you find a molecule that has the critical density or the effective density that you want of the phase of gas you want to study. So CO is a common tracer. It has a very low critical density and basically traces the bulk of the molecular gas in galaxies. And if you want to trace the higher density gas, then you would go for something like HCN or HCO plus that has a much higher density. Probes a much higher density. The critical densities on the left are essentially what you would just kind of naively derive by doing balance with collisions. The effective density on the right is probably more relevant. This has to do with photon trapping because you have considerable optical depth in these molecules. So you're actually probing a lower density and a more extended region in the molecular gas distribution, essentially because your CO molecules or your HCN molecules absorb photons and then re-emit them farther out in the molecular cloud. So if you kind of schematically draw your spherical molecular cloud here, you have your H2 region on the outside, and then at some point the hydrogen becomes neutral. You can kind of probe that with the carbon plus line. And then at some point the hydrogen combines to form molecular hydrogen. You have a rapid transition from ionized carbon to neutral carbon to CO. And that's essentially that CO is where you're probing the molecular gas, the bulk of the gas. And then as you go into the very centers of the clouds, you start to get emission from these dense gas tracers like HCN and HCO plus. So the argument has been historically that you basically pick the high density gas to study star formation. So just to kind of state that in slightly other words, there's a lot of applications of these molecular gas tracers. One is to measure the gas mass in either the total molecular mass or the dense gas. You can also look at the physical conditions in that gas by looking at line ratios or spectral line energy distributions from multiple transitions of CO or other species. And then there's kind of exotic molecules like vibrationally excited HCN, which I'll talk about more in a minute, that can probe very embedded activity. And then of course you also have molecular outflows that you see in CO. So these suite of molecules provide a very versatile probe of the activity and the content of star-forming galaxies and AGN host galaxies. So in terms of HCN specifically, it was observed kind of 10 or 15 years ago that the HCN luminosity correlates very well with the infrared luminosity. And if you think the infrared luminosity is a star formation rate tracer, as is likely in these galaxies, then you basically have a nice correlation between the star formation rate and the mass of dense gas, if you believe that HCN traces that. So this is great because if this is true, you can basically take your HCN observations and learn about star formation in any galaxy, including those that are contaminated by AGN. The wrinkle is that if you look at AGN hosts, that doesn't seem to be the case. So if you just pay attention basically to the x-axis, this is the ratio of HCN to HCO plus. Both of these molecules are ostensibly dense gas tracers. So you would think that if they're both tracing the star-forming gas, you would get a consistent answer between AGN hosts and star-forming hosts. In this figure, the blue points are the star-forming galaxies, and they have an HCN to HCO plus ratio of around 0.5 or 0.7. But the AGN hosts in red are systematically enhanced in HCN or hydrogen cyanide relative to star-forming galaxies. So this is kind of a bummer if you want to study star formation in these galaxies because there's a systematic bias in your dense gas tracer. But yeah.
When you say AGN, do you mean like radio lab or broad lines optical spectra?
These are, I think, well, these are a mix of things. They're kind of more or less BPT optical lines selected, yeah. So I should say that if you look closely at the labels, you'll see that there are not that many systems on there, and the NGC 1068 shows up at least 4 times. So it's a little bit unclear how how robust this particular division is.
So if you just spatially knock out the nucleus, does everything go right back down to the blue area for those same galaxies?
Yeah, typically when you resolve them, you do see the nucleus is enhanced, and then there's a normal star-forming ring on the outside. Yeah. So and then they go back to the kind of 0.7 HCN to HCO plus ratio. So this is bad if you want to use integrated at least, or HCN measurements to study star formation, or if you even want to study star formation in the central part of the nucleus, in the central part of the galaxy. This is great though if you want to find all the buried AGN, because these lines are typically fairly optically thin, so you can see right down to the nucleus. And if you do an HCN to HCO plus survey, maybe you can actually just find all the obscured AGN that would be missed in the optical X-rays, mid-infrared, whichever you like. Another reason you might care about the dense gas tracers is that the fraction of dense to total molecular gas changes depending on the feedback prescription you put into models. So if you can properly calibrate the emission from HCN, you can then convert that into a dense gas mass and basically provide some constraints on feedback models from star formation. And so this figure is showing in red the observations of dense gas fraction against total molecular mass. And then the 4 panels are just showing different feedback prescriptions from the basically the precursor to the fire simulations. So the full treatment is on the left, and then as you remove things like gas heating and winds and then eventually no feedback, you find that the simulations become kind of unable to reproduce the observations. There's a conversion, though, going from HCN to M-dense, so if you're not getting that right, then this becomes a much weaker constraint. So understanding the physics of the excitation of those molecules is very important. So what are those physical processes? This is kind of the list I've seen to date. And this, I could like to divide them into basically excitation and abundance, and then there's also rate transfer effects. In terms of excitation, you basically have to deal with the density of the gas and the UV radiation field that's illuminating the molecular gas clouds. The HCN molecule has a 14 micron absorption band, so if you have a bright infrared source and high column, you can radiatively pump the HCN emission. That'll also, of course, change your line ratios. You can also excite the HCN molecule via collisions with electrons and enhance it that way, via free electron collision. And those are all kind of excitation type effects. And the other broad category of abundance is essentially chemistry. And so you can do that with X-ray radiation. The X-rays penetrate deeply into the clouds and basically heat the interiors of the clouds and drive chemical reactions or ionize species in that dense gas. That will also change your abundances and then your ratios. And also if you kind of heat your cloud uniformly somehow, either with a shock wave or cosmic rays, you can basically change the balance of chemical reactions and promote the creation of different species. So in this case, this is going to be the extent of the chemistry, is you can convert HNC molecules to HCN molecules in warm molecular clouds. So those are isomers, so they have slightly different emission spectra, and you can differentiate them. But basically, this is a way to, again, enhance the abundance of HCN. And all these processes are essentially contenders for trying to explain why AGN have systematically enhanced HCN emission. And then, of course, you have things like radiative trapping, and then you have absorption just from the radiative transfer of getting the line out of the cloud. In terms of the vibrational lines, this is the normal energy spectrum of an HCN molecule. So you have rotational transitions at kind of a few hundred gigahertz and relatively low energy levels. And then there's kind of a cartoon of almost an HCN molecule there on the right. If it absorbs a 14 micron photon, then it starts vibrating in this bending mode and excites this other energy state that's the diagram shown on the left, or sorry, shown on the right. And you can see the energy levels for that energy state are much higher, like 1,000 Kelvin. So it's highly unlikely that you would vibrationally excite HCN molecules thermally in a cloud. So if you see emission from this vibrationally excited species, then you can fairly confidently assume that there's a high column density, very luminous embedded source. So again, that's another way to potentially find buried AGN. In terms of what that infrared pumping looks like, this is kind of a schematic for the organization of that nucleus. You have a hot mid-infrared core that can be several hundred Kelvin, but surrounded by column density of gas, it's maybe at least a few times 10 to the 23, and in some cases up to in excess of 10 to the 25. So that's basically optically thick to out into the far infrared. And you basically reprocess your radiation very easily. You don't see your mid-infrared diagnostics. You're certainly not going to see your optical diagnostics of the AGN. I should note, though, that I have just said mid-infrared core here and not AGN. It's unclear if these are actually AGN or some kind of freakish compact starburst. But anyway, they're extremely luminous and buried behind relatively high columns of gas. And in terms of the effect on the spectrum, this is a kind of toy example showing the effect of that column density on the mid-infrared spectrum, the mid and far infrared spectrum. The dashed line is showing you the intrinsic SED of this compact infrared core, and then the solid line is showing you what the emerging spectrum is after you propagate it through that column density. So you can imagine that even looking with Spitzer or in a few years, hopefully JWST at your favorite neon lines or pH dust carriers, the emission at 10 microns is going to be severely attenuated from these cores, and so you might potentially misdiagnose the activity in these very embedded objects. So the two questions I want to ask are, can we understand the excitation and abundance effects well enough to use HCN to learn about star formation in galaxies? And then kind of empirically, can we use this HCN enhancement to find buried AGN? So I'm going to go through those two things in turn. And the two approaches for the first topic are to either do global studies of the integrated emission from a large number of galaxies in these HCN and HCl plus lines, or do kind of resolved studies of a smaller number of objects and really dig into the details. And I'll go through examples of each of those. So we started out with doing a global survey of HCN to HCl plus in the GOLS galaxies with the IRM 30 meter. So shown here on the middle of a nice ski resort. This is the kind of typical spectra we were able to obtain for a subset of the galaxies. The total sample is about 55 systems. And so you can see that there's a non-detections, detections. There's also a range of HCN to HCl plus ratios just within this kind of infrared selected sample. So these are relatively good data, but again, big beam integrating over the whole galaxy. So the first thing we did essentially is to take that HCN to HCl plus ratio and compare it with mid-infrared diagnostics of the AGN activity. So I'm showing that ratio as a function of the equivalent width of the 6.2 micron PAH feature. This dust feature is thought to be excited from UV radiation from stars. And then the equivalent width is, of course, comparing it to the strength of the underlying continuum. So that means that when you have a high equivalent width, you have a more substantial contribution from star formation to the mid-infrared, and a low equivalent width, you have a strong continuum from an AGN. So things on the left are AGN dominated, things on the right are pure starbursts, and then things in the middle are composite objects. So you do see that, kind of what I showed earlier is that the AGN do have high HCN to HCl plus ratios, kind of 1.5 to 2. The starbursts, on average, have very low ratios around 0.7. The composites are kind of all over the place, but then there's this population of star-forming galaxies that have HCN to HCl plus ratios that are comparable to those of the AGN. So the question is does that mean that these objects have heavily embedded AGN that we're missing in the mid-infrared? Or is there some other property of galaxies that all AGN hosts have and only some starbursts have, maybe some sort of dense gas configuration in the center? So we went through and tried to evaluate all of these physical processes that I mentioned earlier. The first was mid-infrared absorption. We didn't find any evidence for mid-infrared absorption in Spitzer data for those starbursts that have HCN enhancements. But the Spitzer data weren't quite deep enough to really put reliable limits on the absorbing profile. So this is basically a JWST project. In terms of the X-rays, there was no strong correlation of the HCN to HCl plus ratio with any X-ray property that we could reliably measure, such as just the total luminosity or the hardness ratio. So it doesn't seem like X-ray chemistry is driving the line ratio in these objects, at least on a global scale. But we really need more X-ray data. There's kind of limited overlap with Chandra and XMM. In terms of compactness, I just want to take a brief diversion to talk about the C plus to far infrared ratio. So this is a well-known feature of local luminous and ultraluminous galaxies that as you go to high infrared luminosities, the ratio of C plus to far IR drops. This turns out to be very correlated with the infrared luminosity surface density, so basically the compactness of the star formation. And this is only, essentially only showing star-forming galaxies. So I'm going to use the C2 to far infrared ratio as a proxy for compactness, where low C2 to far infrared means more compact starbursts, and high ratios mean fluffier starbursts. So we compared this again to the HCN to HCl plus ratio, and there's kind of a weak and ugly correlation, right? But it really doesn't explain the bulk of the trend. So things that are compact, things on the left, do tend to have higher HCN to HCl plus ratios. But again, there's fluffy things on the right that have a similarly enhanced HCN emission. So compactness may play a role, but it's certainly not the whole story in terms of the excitation of the molecular tracers. Another aspect is mechanical heating, and just to remind, or some sort of cloud-wide heating. And just to remind you that this is a chemical reaction that converts HNC molecules into hydrogen cyanide. So the argument here is that if you, so I'm showing now the HCN to HCl plus ratio against the infrared luminosity surface density. The infrared luminosity surface density is effectively a star formation rate surface density. So it's effectively also a supernova rate surface density. So the argument is that things on the right have much more mechanical energy input into the molecular gas than things on the left. So if this chemical reaction is driving the HCN enhancements, then we should see that as that mechanical heating rate goes up, the HCN to HNC ratio should go down as you deplete the HNC molecules. So we looked at that, and there's essentially no trend there. And I've also circled in red the objects that are HCN enhanced, and there's really, even among the subset of objects, they don't show high HCN to HNC ratios. So again, this kind of suggests that this particular chemical reaction due to temperature increases in clouds is not what's driving the enhancement of hydrogen cyanide on galaxy integrated scales, at least. The problem with this is that HNC is also affected by infrared pumping, and it's easier to pump than HCN. So you could be kind of compensating for an abundance effect by just radiatively enhancing the emission from that molecule. So I think the jury's still a little bit out on this one. So the bad news is that basically after going through all this, there's really no single dominant mechanism for the galaxy integrated emission from dense gas tracers in terms of a physical origin. But now we can start to go look at resolved objects, and this is one example that I did last year called IRS 13120 - 5453. It's an ultraluminous infrared galaxy with a Compton thick AGN in the center that's contributing about 20% of the bolometric luminosity. If you take the AGN out of the infrared luminosity, you estimate the star formation rate is about 170 solar masses a year. This is a compact starburst based on the C+ to far infrared, and it does have this very fast outflow that's seen with Herschel observations of the OH molecule. This is a picture of the galaxy on the right in the HST I band, and you can see it's kind of a merger remnant type thing with a nice kind of diffuse fading tidal tail to the north and messy stellar morphology. The ALMA observations that I'll show cover the area shown in the circle, but essentially the entire molecular ISM is concentrated inside that tiny square at the center, which is about a kiloparsec or 2 kiloparsecs across. So basically taking the entire Milky Way ISM and shoving it into the central regions. This is the band 7 observations, the integrated spectrum for the object. We detect, with very high signal to noise, the HCN and HCO plus lines. If we had HCN vibrationally excited molecules from the infrared pumping, it would show up here. But there's basically no evidence that there's strong infrared pumping in this source. So there's not that kind of bright infrared core. And we can eliminate essentially that possibility of contributing the HCN to HCO plus ratio. So you can see that kind of in a galaxy integrated sense, the HCN to HCO plus ratio is high. It's greater than 1, so that would kind of put it in the AGN camp as far as that diagnostic diagram goes. We did detect the continuum. This is the contour, continuum shown in contours superimposed on the HST I band image again, so it is resolved with ALMA. We can get a size for it. It's about half a kiloparsec across, full width half max. If you take the infrared luminosity and combine that with the size, you get an infrared luminosity surface density that's about 5 times 10 to 12 solar luminosities per square kiloparsec. That's quite high, but it's actually still below the kind of Eddington limited star formation models, considering the gas fraction and the velocity dispersion of this system. So it's a vigorously star-forming thing with a very high luminosity surface density, but it's not really in any danger of kind of blowing itself apart. This is the HCN to HCO plus ratio map now. I'm getting to what Barry was asking about. And you can see at the center, the ratio is about 3, so quite high. And then on the outskirts, there's this more normal star-forming disk with a HCN to HCO plus ratio of 1. And just to remind you that there was no infrared pumping detected, but using the star formation rate, we can predict a supernova rate, which should be about a little more than 1 supernova per year inside that central 500 parsecs. And then if you work out what you expect for mechanical energy input from the supernovae at that rate, this enhancement in the center is basically consistent with enhanced chemical abundance from that conversion of HNC molecules into HCN molecules. I won't say that this is the final word on this. This is only one transition, so we can't really reliably separate abundance and excitation effects. But at least this is a consistent argument that shock heating of clouds or mechanical heating of clouds can produce these enhancements in the center, and that we basically don't have to rely on any AGN to explain the line ratios.
Could you detect the supernova activity at that rate?
They would be incredibly buried. You might be able to try and do it with VLBI if you look for radio supernovae.
Done in
Yeah, and ARP 220 as well. There is a near infrared campaign with Gemini, I think, to look at some of these infrared objects and look for supernovae on relatively short timescales.
One a year, you might stand a chance of things.
Right. Yeah. So they do see kind of not quite one a year. I think the ones they're looking at are more like a quarter or a half per year, and they do see them, so it's possible. For this particular one, I'd have to go back and look at what the column densities are, to the star-forming disk and see if you could reasonably detect them in the near infrared. So, yeah. So that was kind of a potentially, unsatisfying answer about the excitation of these molecules and understanding the physics of what's happening. But now I want to turn to this other question, which is, can we use this line ratio as an empirical tool for finding buried AGN? And so with that in mind, we went and proposed for NuSTAR observations. NuSTAR is the first imaging hard X-ray telescope. It covers 3 to 80 keV. And the nice thing about this is that above 10 keV, you still get X-rays through relatively high column gas. So even Compton-thick objects will still show some hard X-ray emission, kind of the 20 to 30 keV band and above. So the idea here is basically quite simple. You basically take these 4 objects that have HCN enhancements, but look like starbursts in the mid-infrared, and go observe them with NuSTAR and see if you find a heavily obscured AGN in those galaxies. This is the first observation that was delivered, a kind of nondescript luminous infrared galaxy, NGC 5104, 2 times 10 to the 11 solar luminosity, so forming 10, 20 solar masses a year of stars. Firmly a star-forming galaxy based on the mid-infrared diagnostic, at least the pH equivalent width, but it does have this high HCN to HCl plus ratio. So we pointed NuSTAR at it, got a beautiful spectrum here with a power law of 1.7, but it's actually a blazar that's right next to it. So we got a nice detection of the blazar, and the blazar not even doing anything interesting. It's not flaring, it's just hanging out. But this is what NGC 5104, where it should be. So no hard X-ray detection. And you might say, well, those column densities are pretty high. Would you actually detect it? This is what we predicted for the NuSTAR observation for a 10 to the 24 column density AGN with 1% of the bolometric luminosity. So we're really digging quite deep into the energy source of this system with NuSTAR. And we essentially have no evidence there's a black hole or an active black hole in the system. Just to show another one, this is another IRAS galaxy, slightly more infrared luminous. This one has a pH equivalent width which is much lower, kind of consistent with a composite source where you would expect there to be an AGN. Still has this high HCN to HCl plus ratio. So this one we kind of figured we would see an AGN in the center. And we see hard X-ray emission here. This one's actually believably detected. And there's the spectrum on the right. The 2 lines are essentially the 2 imaging cameras with NuSTAR. So you get kind of a binary or a confirmation on your detection. Unfortunately, this X-ray spectrum is entirely consistent with X-ray binaries in the galaxy, just purely from the star formation. So despite the fact that we get some hard X-ray, it's basically consistent with the star formation in the system. So now that all 4 of the objects have been observed, we have the one detection of that IRAS galaxy that is consistent with star formation. And then we have 3 non-detections of the other systems. So we can go through and now make upper limits on what the AGN luminosity should be relative to the infrared luminosity. These are 1 sigma limits for column densities of 10 to the 24 and 10 to the 25. And you can see that if, for a Compton-thick object, the AGN can't be contributing more than 1% to the infrared luminosity. If you go to higher column densities, you can start to get a few tens of % contribution. You can hide that. But it's certainly not dominating the energy output of the galaxy. So I think I can kind of firmly say or convincingly say that this HCN to HCl plus ratio is not really a reliable tracer of AGN, at least not any AGN that matters in a galaxy. So to kind of summarize that, the main physical driving mechanism is really uncertain. People seem to kind of be converging on mechanical heating, but I don't think the job's done yet. But then in terms of the X-ray observations, there's basically no strong evidence that this line ratio is a useful or reliable AGN diagnostic. So I want to talk now about simulation effort and this ground truthing that I mentioned before. And I've been thinking basically how do we interpret modeling observations of very complicated systems and come up with modeling of spectral line energy distributions from CO or other complicated systems like that. And the issues are really that you're spatially averaging across sources. Within your beam, you're combining a whole range of properties. You have a kind of a continuous distribution of all these properties, but you're picking one value that you're trying to model, right? You get 1 temperature out, maybe 2 temperatures if you're lucky and you have a lot of data and you can do a multi-component fit. Then we really want mass-weighted quantities because that's what we care about in the galaxy, but we're looking at emission, right? So we typically get luminosity-weighted quantities. And then you have this issue of a single component model. And so the question is, how are we getting back anything sensible when we model observations in a detailed modeling? So the definition of ground truth here, if you haven't been exposed to this term, is basically factual data that you got through direct observation as opposed to remote sensing. So obviously we all do remote sensing. The Landsat folks handle this by basically, as the Landsat satellite flies overhead, someone rows their boat out into the lake and sticks a thermometer in the lake, and then they can calibrate the temperature, right? So we'd like to do that. We can't. So what I'm going to try and do is run hydrodynamic simulations and then create synthetic observations. Then I observe these simulations, apply standard analysis techniques and modeling techniques, get out some parameters for the model, temperature and gas density, for example. And then I go back into the simulation and say, am I getting anything remotely related to what's in the simulation? So these detailed hydrodynamic simulations basically capture a lot of the relevant galaxy formation physics in terms of star formation, hierarchical assembly, feedback, things like that. But the point isn't necessarily that these are perfect simulations of galaxy evolution. It's just that they're realistic enough that we can apply synthetic observations and check if our observational techniques are doing what we think they should. So I want to go back to the main sequence here. And this is now showing a kind of consensus main sequence star formation rate as a function of stellar mass for a range of redshifts going from 0 to up to 4. And so you can see that basically for a fixed stellar mass, the star formation rate is much higher for a galaxy at that mass at higher redshift. So the question that we want to answer, I guess, is why is this main sequence moving up with higher redshift? Is it because the galaxies are forming stars more efficiently? Is it because because there's more gas in the galaxies, or some combination of those? Oh, yeah. So, so Nick has been looking at this with Cosmos and ALMA observations and basically finding that it's some joint combination. This is the change in the main sequence as a function of redshift, and it's compared to the change in the ISM mass and compared to the star formation efficiency. And so both of these things are contributing, but basically the interstellar medium mass seems to be the more significantly evolving quantity. So these measurements, the gas masses were obtained by using dust as a tracer of the ISM mass. And if you basically, in the optically thin Rayleigh-Jeans limit, the luminosity, monochromatic luminosity in the far infrared or the millimeter is just proportional to the dust temperature and the dust mass. So if you divide the whole thing by the gas mass and then say that basically these constants in front and the dust emissivity are roughly constant between galaxies, and then the dust temperature doesn't change much between galaxies, and the gas-to-dust ratio doesn't change between galaxies, then the specific luminosity in the Rayleigh-Jeans tail as a ratio of the gas mass should be some sort of constant. So that's cool, because if you can go observe the dust emission, this is relatively quick to do with ALMA. If there's a constant conversion, you can just immediately get your gas mass from a very short observation. And as Nick will say, this takes minutes with ALMA instead of kind of half an hour in CO. Nick calibrated this. This is the ratio of the 850 micron luminosity to the molecular mass as a function of the 850 micron luminosity. It's pretty much flat, and so you can argue that basically there's a constant conversion between these two quantities. So the question I want to ask from the simulation standpoint is, does this work, and then how far can we push it? There's a lot of possible complications here. One is that the CO conversion factor may change between galaxies. In order to get in order to calibrate that, you have to assume a CO conversion factor to get a mass. The dust temperature from galaxies does change somewhat. Metallicity changes galaxy to galaxy. And then this is also calibrated on massive galaxies. So these are all kind of areas where you might think it could, run into issues. So the way we approach this was use cosmological zoom simulations. And the procedure for this, if you're not familiar with it, is basically to run a dark matter-only cosmological simulation down to redshift 2 or redshift 0, whatever your redshift of interest is. Then you go find a halo that's the halo mass that you're interested in, figure out all the particles that went into that halo, follow them back to the start of the simulation, cut out that box, and resimulate that box at much higher resolution with hydrodynamics and feedback and all your favorite physical prescriptions. So we do that, and then we run radiative transfer processing on those snapshots to generate an SED for each galaxy in these zoom simulations. And we run several zoom simulations as well. So this is one example. This is Halo 104 going from redshift 5 down to redshift 0. This is the projected gas density distribution. And on the right, I'm showing the evolution of stellar mass, molecular mass, atomic mass, and dust mass for 7 different halos as a function of redshift. And apologies to the theorists where I've switched the redshift axis there, but time going right to left. So you can basically see that we have all these relevant properties from the galaxy just from the simulation. The radiative transfer post-processing means we have the SEDs. So we went and measured the 850 micron luminosity and then compared to the molecular mass in the simulation. And the triangles here are the calibration points, and now all the colored circles are our data points from the simulations. And it's basically beautiful agreement here. So in our simulations, the observed 850 micron luminosity recovers the molecular mass to within about 0.2 dex, which is really quite pleasant for how much faster and easier it is to do dust continuum. We have a slight preference for this luminosity-dependent calibration versus a purely constant calibration, but that's a little bit, that's kind of a low-level thing. But what is the scatter dependent on? So we look through that with the simulation properties. This is showing the ratio of the molecular mass we infer from the dust emission to the true molecular mass from the simulations. And now here I'm showing this as a function of the mass-weighted dust temperature of the galaxy. And you can basically see there's no correlation there. So dust temperature does not seem to be driving the scatter in this relation. This is now comparing against the dust mass. Again, no real clear correlation, maybe a slight uptrend, but dust mass is not driving the scatter. It turns out actually the gas-to-dust ratio is very strongly correlated with the scatter. So basically as you build up dust mass, you kind of fall onto the relation in these systems. So that's, you could say, okay, cool, I can go measure the gas-to-dust ratio, but you're trying to figure out the gas mass. So you can't do that without knowing it ahead of time. You could probably go and get the metallicity of the galaxy and then assume a metallicity gas-to-dust ratio relation and do that. It's not clear to me that that will reduce your scatter any. You probably just add different scatter. So I don't know which kind of scatter you like, but. So another thing though is in this treatment on the left here, we basically assume that a fixed fraction of the metal mass is locked up in dust. We know from dwarf galaxies in the local universe that that's probably not true, and that as you go down in metallicity, you actually lose twice. You have fewer metals to make dust, and then a smaller fraction of those metals are locked up in dust. So we also implemented a variable dust to metals model, kind of mimicking the closest approximation to observations we had. And now this is color coding the same simulations, but by their metallicity with this variable dust to metals ratio. And you can see that once you get to about, minus 0.8 in log metallicity over solar, things start to fall off the relation. So for low metallicity galaxies, you're probably not going to get the molecular mass right because the dust mass is much lower. The good news is actually you can't observe any of these things. So it's probably safe from the standpoint of going out and observing at redshift 2 to 4 and measuring the dust mass to get a molecular gas mass. But just keep that in mind if you start looking at really lens things and throwing a lot of ALMA time at stuff. So the summary for that is that the 850 micron luminosity is a good predictor of the molecular mass for solar metallicity galaxies. I didn't mention this, I can talk about it later if people are interested, but you have to pick an observing band because you usually can't observe the rest frame 850 micron luminosity or the flux. But if you do it right, it's only a 10 to 20% scatter, so it's completely manageable. And then again, kind of worry about this thing when you're getting to low metallicity. So in the last few minutes, I want to talk about the effect of mergers on dwarf galaxies, and I'll start out by showing this often shown scenario for massive galaxies that seems to be more or less widely accepted and empirically supported. And the scenario right is you have galaxies, isolated galaxies, they come together in small groups. They may undergo an interaction, get these tidal tails. Dynamical friction in the dark matter halo causes the two galaxies to merge. You get a coalescence, a lot of gas funneled to the nucleus, and you get a starburst phase. At some point, you presumably start to feed some gas onto the black hole. You get a very luminous AGN. the combination of the AGN and the star formation conspire to blow out the gas or consume it. You expose the quasar, and then either by, again, consumption or blowout of gas, you deplete the star formation fuel in the galaxy. Your stellar population ages, the galaxy dynamically relaxes, and after a period of time, you end up with a red and dead elliptical galaxy. So this is kind of the scenario, right, for massive galaxies. And you can run a simulation for that with whatever feedback prescriptions and fueling prescriptions you like, and essentially recover the salient features. So I think this is the state of things for dwarf galaxies. We know there are dwarf galaxies. Sabrina found dwarf groups, so we know they're dwarf groups. We can see dwarf interactions and mergers, I mean, even just like the LMC or NGC 44, 85, and 90. But I would say that basically all of this stuff, we really have no idea if the same scenario applies to dwarf galaxies. So, well, presumably they coalesce, but we don't know what kind of starburst they create when they coalesce. We don't actually know if there's black holes in most of them, so you don't know if there's going to be an AGN phase. These things are so gas rich that you may actually not be able to blow out and remove all the fuel, in which case you won't go through this decay phase. You'll go back here to kind of nice star-forming isolated dwarf galaxy. And so you may not actually produce quenched dwarf galaxies in the field. And that's supported observationally, at least, the lack of quenched dwarf galaxies. This is the quenched fraction as a function of stellar mass. You can see that around a few times 10 to the 9, you basically stop having quenched dwarf galaxies in the field. So this suggests that quenching process does not operate. I mean, presumably some of these things are merging. So, they can't all, well, this suggests that the merging process doesn't result in quenched galaxies. We do, however, see enhanced star formation in pairs, and this is some work that Sabrina has done. This is the enhancement compared to control galaxies as a function of pair separation for massive galaxies and dwarf pairs. So you can see that dwarf galaxies also form stars more efficiently or rapidly in interactions, or at least in pairs, similar to massive galaxies, and actually perhaps slightly more efficiently. I mean, it'd be nice to get some more dwarf galaxies and show that, but it's certainly, consistent with the errors. So we have kind of these aspects that are, this is similar to massive galaxies. This is different from massive galaxies, whether you quench things or not. So in order to look at that, we've been constructing a sample of dwarf galaxy pairs. This is the Tiny Titan survey that I also mentioned this morning. It's a Sloan-selected sample of pairs ranging in stellar mass from 10 to the 7 to 5 times 10 to the 9. The selection criteria for the pairs is to basically be isolated from a massive host, and that means a velocity separation and a projected physical separation. And then we also require the dwarf pairs to be reasonably likely to be physically associated. This is a kind of a few examples here of dwarf pairs. Some of them are a little bit harder to see. And we are building up a multi-wavelength data set with Sloan imaging, H1 observations, X-rays, and H-alpha imaging. And I'm going to briefly talk about a VLT Muse program that we are just getting kicked off on the TNT dwarf galaxies. But I should say that this isolated pair sample is also complemented by a pair sample that is associated with a massive galaxy. And then both of those samples are also matched in unpaired dwarfs. So with these kind of 4 subsets, we can really tease apart the effect of interactions and environments on the evolution of dwarf galaxies. So this is the one particular object that we have Muse observations for. Again, Sloan selected, looks kind of like a mess. It's a very low redshift, stellar mass about 10 to the 8. If you take these, this galaxy and this galaxy, the stellar mass ratio is about 4 to 1. The gas fraction is uncertain because we don't have resolved H1 measurements yet, but it's almost certainly above 40% and probably closer to 60% for this system. It's pretty clearly subsolar metallicity, so I think this is probing an interesting regime of galaxy formation, in some ways analogous to high redshift galaxies, epoch of reionization galaxies, the low metallicity, the very high gas fractions, and of course the kind of hierarchical formation. So we want to ask what's the effect of mergers on the dwarf galaxies. So this is a red image from the VLT. The blue line is showing that separation we chose for the 2 galaxies. The red circles are showing where the Sloan fibers are, and we basically recover the separation, velocity separation with the Muse data. So because Muse is, of course, a nice wide field IFU, we can make star formation H-alpha maps and then convert those to star formation rates. This particular system has a whopping star formation rate of half a solar mass a year. But it turns out that for this stellar mass, that's a factor of 10 over the main sequence at 10 to the 8. So this thing is forming stars at an incredible rate for its tiny size. The secondary galaxy actually has a star formation rate enhancement that's closer to a factor of 60 for its stellar mass. So this thing, yeah, for its size, forming stars incredibly quickly. You can see clumps of H alpha in the image. So the star formation is clumpy, but essentially the brightest 3 clumps contribute less than about 30% of the total flux and therefore the total star formation rate. So the star formation is clumpy, but it's basically extended over the whole galaxy. This is in contrast to massive mergers where you typically see the starburst in the very center where gas has been funneled into the middle. But this doesn't seem to be the case for this object. In terms of excitation, if you look at kind of line diagnostic diagrams, everything is consistent with star formation. There's no real evidence of AGN or even major shock contribution to the ISM excitation. So we didn't find a kind of a cool black hole in this thing. But that kind of supports the use of H alpha as a star formation rate indicator. So the scenario we have for this is that dwarf galaxies have these large H1 envelopes, right? And so if the 2 dwarf galaxies come together and interact, instead of funneling gas to the centers, their H1 envelopes basically run into each other. And you squeeze the H1 envelopes of both galaxies, and you basically force the pre-existing molecular clouds to collapse. So you push them together, squeeze the envelopes, and then all the molecular clouds in the galaxy kind of pop off, no matter wherever they are at the time. So rather than gas funneling, it's a kind of a compression scenario for triggering the starburst in this system. That lack of funneling potentially has impact on the future evolution of the system. You may not you may not have significant bulge growth in a galaxy like that if you're not funneling gas to the center. You're just kind of building up stellar mass in whatever pseudo-disk thing it can form. That has impact for the bulge, but also there's potentially less black hole fueling that will happen because, again, not funneling as much gas to the center. That's, of course, kind of predicated on whether there is a black hole in the galaxy at all. But if there is one, it's certainly not. It's certainly going hungry, I guess. So in terms of all there's areas, I think there's very obvious paths forward. And one is to look at this molecular gas-dust luminosity relation and see where it breaks down. So now we have a cycle 6 ALMA program for the tiny Titans galaxies to observe them in the dust continuum to basically measure the dust luminosity of these very low mass, low metallicity dwarf galaxies and try and use that to estimate the molecular gas mass and see how this holds together. The observation of the dwarf pair, I think, was very tantalizing by virtue of the fact that it suggests that dwarf galaxy mergers may behave significantly different than massive galaxy mergers. And this, of course, has impacts for structural formation of those galaxies. And then to the degree that you can use local dwarf galaxies as analogs for high redshift systems, this may be useful for learning about how proto-galaxies are assembling and forming. So we have a VLT Muse program to do an additional 7 dwarf pairs that will hopefully see if this is a common phenomena or if that was the common prototypical thing that's interesting and the rest of the class is boring. And then on the molecular gas side, we have, there's a larger and larger number of objects being observed in these lines with ALMA to the point where we can now build up multi-object, multi-transition studies of these systems, all resolved. So this will be actually great for disentangling this question of abundance effects versus excitation effects. So I think in the next few years, we'll be able to really apply that kind of detailed modeling to these systems and really figure out what the molecular gas tracers are doing. And then, of course, JWST will be coming along before too long. And that will be great for high-resolution mid-infrared diagnostics. Both of the AGN tracers that are classically used in these systems, applying to these systems, but also that HCN absorption at 14 microns will, of course, fall right into the MIRI IFU wavelength range. So you'll be able to study the absorption feature for the vibrationally excited HCN molecules simultaneously with, with the millimeter observation studying the emission. And I think that'll provide a very powerful probe into the heavily embedded regions that we really can't seem to probe with even, hard X-rays. So I think that'll be something good to watch. And then, of course, lastly, with things like the 30-meter and LSST, we'll be able to find a lot more dwarf galaxies out to, higher redshifts, build up larger samples of these objects, and, detailed follow-up will really, I think, tell us more about how low metallicity star formation happens, which we can then, of course, bootstrap to high redshift and complement observations there. So to kind of wrap up everything and summarize, the link between globally enhanced HCN emission and the AGN activity is complicated. The HCN enhancements are not a reliable tracer of buried AGN, so I wouldn't hang your hat on that if you need to find all the buried AGN. And then the driving physics is really uncertain. People seem to be kind of converging on shocks or some sort of cloud heating, but I don't think we really have enough data to say for sure. Based on this ground truth study with hydrodynamic simulations, the use of the 850 micron luminosity as a molecular gas mass estimator seems essentially secure for the things that we can actually detect. If we start to really go deep or use lensing, then of course that might be a little more hairy. And then lastly, the dwarf galaxy pairs, the first one shows this kind of interesting distributed starburst, and it's not clear if that is a generic feature, but if it is, it might suggest there's ineffective gas funneling and that these mergers affect dwarf galaxies in an important and different way compared to massive galaxies. Thank you.
Thank you very much for a wonderful talk. Questions?
So George, the IFU studies are kind of interesting. I mean, that source didn't look like they had a lot of shocks, but there are dwarf galaxies that do look like they have shocks and outflows.
Right.
Universe. So it seems to be a much more diverse population in terms of polluting the IGM from dwarf galaxies like that. So I think these kinds of studies with news will be very interesting in that kind of aspect as well, not just for the funneling, but also for the ecosystem.
Yeah, definitely.
So, I mean, are there other big programs that are happening besides the one that you guys are doing, or?
Specifically focused on dwarf galaxies. Yeah. There's kind of there's dwarf galaxies in clusters that are being followed up with MUSE, I know, and I'm sure there's also isolated, more nearby dwarf galaxies that are being studied, yeah. But I think as far as I know, we're the only ones doing the pairs. So I think you'd be maybe less likely to catch the starbursting things in an isolated sample, but yeah, presumably there's some in there.
Other questions? If I may, please.
So in any items with the survey of the dwarf galaxy pairs, do any of those show evidence for AGN from other indicators?
So there's suggestions that are, I guess I would say at this point, kind of uncertain. So there are systems with red WISE colors that for massive galaxies that's been interpreted as an AGN indicator. Sabrina will know more than this, but basically the X-ray follow-up has not been good to us in terms of finding AGN there. I don't think any of the Sloan spectra we have any evidence for AGN based on like BPT line ratios, diagnostic line ratios. There's a system with a hard X-ray source, but it's unclear if that's an AGN or, again, X-ray binaries. So we don't have any conclusive things. There are some tantalizing hints, but yeah, no real confirmed AGN so far.
Are any of the ones with hints of AGN in your sample to follow up with you?
Yes, the one with the hard X-ray observations is, so. Yeah.
Other questions, Barry?
In all of this, where would you draw NGC 3077 and M82? Are they not dwarf enough? They're not pairs. They're
Right.
in a group, but how do they fall into this scenario?
I guess I would say that the star formation seems more compact in M82 compared, the starburst is. So presumably that it's massive enough. It's massive enough that it has the H1 fraction may be low enough that you can efficiently funnel gas. You don't get it's not really hydrodynamic stalling, but gas funneling seems to be less efficient in high gas fraction systems. So in that case, there was two things going on, right? It's massive enough that it probably has a relatively low gas fraction. Then it's also interacting with a much more massive thing. So I think that's kind of the difference. These things are low mass, high gas fraction, much more comparable. So I would suspect that's why there's perhaps a little bit more gas funneling. Yes, yeah, certainly, yeah.
Question, Nick?
I was under the impression that in dwarf galaxies, the starbursts were fairly localized within the galaxy, whereas your models would seem to trigger a starburst over the whole galaxy.
Well, so, I mean, that's based on just the observations. I haven't really seen a lot of models specific to that. I think like fire doesn't really go down to this mass range very much. Yeah.
The observations.
Yeah, yeah.
I think showed localized, high rates of star formation, but then large amount of neutral gas around that.
Right, yeah, so that, I mean, that might be a difference between pairs and isolated dwarfs. If, the isolated dwarfs, presumably molecular clouds kind of pop off pseudo-stochastically without regard for the environment. But in the pairs, you have this external force, this external compression of the ISM that's basically pushing all those clouds to pop off earlier than they might otherwise have in isolation.
Any other questions? It's hard to see from here. If I may quickly ask, if I understood right, when you did the new star observations, you had 4 objects and 3 were bummers.
Yeah.
Those 3, you showed energy distributions, but they were normalized, so one didn't see the scale. My question is the argument that they don't have AGNs based on the shape of the energy distribution or on the flux, and then the statement that there's enough star formation to reproduce it?
This one right here, right?
Yes.
Yeah. So the point crosses here are the observations. Beautiful typical X-ray spectrum. The lines are the model fits by taking some sort of star formation rate, converting that to an X-ray binary population, and then predicting what or basically doing the hard X-ray contribution. I mean, you see it's not really that hard either, right? It's like 6 to 12 keV or something, so it's not super hard.
Great, thank you. Any other questions? If not, let's thank our speaker again.